for attending our talk about ChaosDB, an account takeover vulnerability we found in one of Azure's most popular databases solution, Cosmos DB. So just a quick who are we before we begin. My name is Sagi, and here with me is Nir.
Hey.
We're both security researchers from Wiz Research Team, and our team vision is to uncover new attack vectors in the cloud. Our team also presented in the last Black Hat and DEF CON events, and these are the talks that we gave. And generally, we do cloud security research and publish our findings on our blog. And here are a couple of our most recent publications. Note that we are also planning to disclose more vulnerabilities soon, so stay tuned about our blog. OK, so in August 2021, we reported Microsoft a cross-account vulnerability that we found in its Cosmos DB service. Exploiting this vulnerability essentially allows any attacker to completely compromise Cosmos DB databases of other customers. This vulnerability got a lot of attention. And today, for the very first time, we are going to disclose all of the technical information behind this vulnerability, including how we even managed to get some access to Azure internal infrastructure. But before we dive into the technical details, let's go over the agenda for today. So we will first talk about what is Cosmos DB and our motivation for this research. Then we will walk you through the technical details of the first two bugs that we found in the service. Then we will uncover some new information regarding an Azure internal component called the WireServer. And with this new information in mind, we'll discuss the third bug and how we chained all of these bugs together for an account takeover vulnerability. Then we'll show you a demonstration of our full exploit from unauthorized attacker to a complete database compromise. And we'll finish up with a summary regarding everything that we've learned during this research and our conclusions. Hopefully, by the end of this talk, you will have a better understanding of Azure architecture in general and Cosmos DB specifically, and you will also understand how we exploited multiple flaws in this architecture in order to achieve an account takeover vulnerability. OK, so let's talk about our motivation and why did we choose to research Cosmos DB specifically. So Cosmos DB is a managed database solution offered by Azure. This means that if you are an Azure customer and you need a database for your application, you will most likely use Cosmos DB. And it turns out that this service is very popular among Azure customers. You can see in this picture that there are some very big companies that are using Cosmos DB. Being a popular database solution, this makes Cosmos DB the holy grail for attackers. Everything an attacker wants from your organization is usually stored in some sort of a database. And for that reason, we thought that if we will find a vulnerability in Cosmos DB, it will have a lot of impact. But if we are being completely honest, we didn't even intend to find a vulnerability in Cosmos DB. We were originally looking for common misconfigurations that a customer can make when they set up their Cosmos DB account, so that we at Wiz will be able to alert our customers regarding such misconfigurations. OK, so as I mentioned before, at this point, we are not looking for vulnerabilities. We were simply scanning the features that this service has to offer to see what can be misconfigured. We quickly noticed that Cosmos DB comes bundled with another product called Jupyter Notebook. And for those of you who don't know what Jupyter Notebook is, it looks something like this. Generally, Jupyter Notebook is a web application that lets you represent your data using code. And Cosmos DB users use these Jupyter Notebooks in order to explore and analyze their data. Because we were already familiar with Jupyter Notebook, we knew that it lets its users execute arbitrary code in different programming languages. And this raised multiple questions for us, like, where is this code actually running? And who owns the machine that this code runs on? Maybe this machine is shared across users, or it may be able to access some interesting resources. So let's talk about the first bug that we found in the service. We started digging into the Jupyter Notebook feature, and we quickly found out that we are actually running inside a Docker container using a low-privileged user named Cosmos User. And you can see in that picture that it has the UID of 9000 and GID of 9000. Now, this service even offers a more comfortable way for executing code in the form of an embedded web terminal. And you can see that, unfortunately, we are still running as this low-privileged user there. Now, we did perform some basic recon using this user, but there were still a lot of things that we wanted to access but couldn't. And this got us wondering, how hard would it actually be to obtain root privileges on this machine? So after clicking on enough buttons in the web interface, we actually found a way to elevate our privileges to root. Turns out that all we had to do in order to obtain root privileges was to simply switch the programming language from Python 3, the default, to C#. And any code that is executed via the C# notebook actually runs with root privileges. Now, this has an explanation. In the backend, every programming language has its own host process. And while the host process for the Python 3 programming language runs with the expected Cosmos user, the host process for the C# programming language specifically runs with root privileges. And we can abuse this feature by executing this local privilege escalation payload, which edits the etc password file and append an entry for the root number 2 user, which will have the UID and GID of 0, effectively granting us root privileges inside this container. OK, so let's see this bug in action. OK, so what you can now see on screen is me setting up a Jupyter Notebook and executing the ID command in the embedded web terminal. And you can see that we are running as Cosmos user. I will also execute the ID command via the Python 3 programming language. And you can see that we are still running as this Cosmos user. And all we have to do in order to elevate our privileges to root is to simply click on this menu, switch the programming language to C#, and any code that will be executed in this context will actually run with root privileges. So we paste our local privilege escalation payload, execute it, and now we can return back to the embedded web terminal in order to obtain our root privileges by simply switching to the root number 2 user. So let's do just that. And we have root privileges inside our container. OK. So now that we are done with bug number 1, let's continue to the next bug. Since we are now having root privileges inside this container, this means that we can perform a more extensive recon and try to answer some of our unanswered questions from earlier. So one of the commands that we issued was the iptables-nvl command in order to view the local firewall rules configured on this machine, which may indicate which network resources we can access and which we shouldn't be able to. And you can see that there are a couple of interesting rules here, so let's talk about them. The first rule is this rule, which should prevent us from accessing the IMDS, also known as the metadata service. Now, for those of you who are not familiar with the IMDS, it is actually a service that you can query using HTTP in order to retrieve metadata information regarding your VM instance. And for some reason, the developers of the Jupyter Notebook feature do not actually want us to access it. Another interesting rule here is this rule that prevents us from accessing the 10.0.0/16 subnet. Now, at this point of this research, we have no idea what this subnet is. All we know about it is that this is a subnet of internal IP addresses and that we shouldn't be able to access it. Finally, there is this rule that prevents us from accessing this very specific IP address. Now, same as before, we have no idea what this IP address actually is. All we know about it is that the developers do not want us to access it. But the good thing is that these are local firewall rules that were configured using IP tables, and we are now running with root privileges. This means that there is nothing that prevents us from actually removing these rules and accessing these network resources. And as you can see, by simply issuing iptables-f, we completely remove these rules, and now we can explore these resources. Now, as an attacker, this makes me quite excited. We just removed the one thing that prevented us from accessing network resources that we know for a fact that the developers of the service explicitly tried to forbid us from accessing. And in our opinion, these rules should be enforced outside of the container, where a privileged attacker can't even touch them or remove them. OK, so now that we remove the local firewall rules, this means that we can access the IMDS. And given we are not supposed to access the IMDS, we want to see why. So this is us querying the IMDS and the response that we got back. And there are a couple of interesting things here. First, our Azure environment is set to Azure Public Cloud, and the subscription ID is not a subscription ID that we own. Now, this may indicate that we are running in some sort of a shared environment, and that we are not the one paying for this virtual machine. Another interesting thing here is that our OS type is set to Windows. Now, this is strange. We are obviously running Linux commands in a Linux terminal, so why is it set to Windows? After digging a bit more into our environment, we actually concluded that we are querying our host machine metadata service and not the metadata service of our container, and that our host machine is actually a Windows virtual machine hosting this container using Hyper-V. The last thing that you cannot see in this picture is that according to the IMDS, we also have an IP address in the 10.0.0/16 subnet. And just to remind you, this is the same subnet we shouldn't be able to access according to the local firewall rules we just removed. Okay, so let's quickly recap everything that we achieved so far. First, we set up a Jupyter Notebook container for our Cosmos DB account, and we jailbreak it by obtaining root privileges in it and removing the local firewall rules. Then we queried the IMDS and learned two things. The first thing is that this virtual machine is hosted on Azure, and most likely in some sort of a shared environment. And the other thing is that our host machine is a Windows virtual machine, and we can query its resources. I will now hand it over to Nir to continue explaining about our Recon environment.
Thank you, Sagi. Let's continue on our network Recon. If we'll have another look at the machine IP table rules, there's that mysterious IP address. What is this IP address? When we searched this IP address on Google, we found this MSDN article. According to this article, this is a virtual IP address that exists on every Azure virtual machine, and it has a name, the WireServer. So what does the Microsoft documentation say about this mysterious endpoint called the WireServer? First, we know it's a server that is accessible in HTTP, and that this server manages the extensions of every Azure virtual machine. Extensions are just software applications that Azure manages. They can be first-party software, like Azure's Log Analytics agent, or third-party software that Azure supports, for example, Datadog. Whenever a customer installs an extension via the Azure portal, the WireServer instructs the virtual machine's agent to install the extension, supplying the appropriate configuration. That configuration may even include sensitive information, and any information we can extract from the WireServer will help us to better understand the underlying virtual machine and the environment we are running in. But after looking at all of the documentation that Microsoft has to offer about the WireServer, what is most evident is that this server has little to no documentation. But there's a silver lining. The WireServer has two clients designed to install and configure extensions based on the information fetched from this server, the Linux and Windows virtual machine agents. The Linux agent, also known as the WA agent or the WA Linux agent, is an open source project hosted on GitHub. Maybe by reading the source code of the Linux agent, we'll be able to learn something about the WireServer's functionalities. It is also worth mentioning that some of our WireServer research is based on the work of another security researcher, Paul Litvak from Intezer. Paul already conducted a high-quality research regarding this topic and detailed it in a great blog post. So to recap, we can think about the WireServer as the backend of the WA agent, the Linux virtual machine agent. It is used to supply the agent all the information it needs in order to function properly. So with that in mind, let's examine how the WA agent gets its extension information from the WireServer. Before the agent can retrieve any configurations, let alone extension configuration, it must first fetch something called the goal state. The goal state is, among other things, is a phone book of endpoints that the agents need to contact in order to fetch different configuration settings. Note that you can download any Azure virtual machine goal state by executing the following CRL command and get all the configuration endpoints specific for your Azure virtual machine. Now, here's the response we got executing the CRL command on our Azure Linux virtual machine we set up for testing. Here you can see that it contains a bunch of different URLs, but the URL we care about is the extension configuration URL that contains all the configuration settings of the virtual machine's extension. Now, we were initially forbidden from accessing the WireServer because of the local firewall rules, but now we can start fetching information. Let's try to execute the exact same CRL command on the Jupyter Notebook container and get back the underlying virtual machine's goal state, including its extension configuration URL. Now, after getting back the extension configuration URL, let's try to access it as well. Okay, so here's an example of an extensions configuration from a Linux-based virtual machine, specifically the Linux diagnostic extension. Each extension has two main configuration parts. There's the public settings section, which is now highlighted in red, which contains public data without any sensitive information. And there's also a protected settings section, which is encrypted, and therefore we suspect it might contain sensitive information. Shown on screen is the Linux diagnostic base64 encoded, encrypted, protected settings. Now, let's try to get the underlying Azure virtual machine extension information. Remember that although we're running inside of a Linux environment, the extension information we are pulling off the WireServer is of the host Windows virtual machine. And here you can see that our host Windows virtual machine has the DSMS for Windows extension, which also has a protected settings section. And as I mentioned before, the protected settings are encrypted, and therefore we suspect they might contain sensitive information. So we decided to try and decrypt them. Let's see how the agent itself decrypts the protected settings. Where does the agent get the decryption key from? Well, similar to the extension configuration endpoint, there is a certificates endpoint that the agent needs to contact in order to fetch the keys required for decryption. This endpoint also can be found in the machine's goal state we fetched earlier. Now, these certificates are the golden key used to decrypt all sensitive protected settings, making them themselves sensitive information. You wouldn't transfer them in unencrypted communication, right? The way the agent protects these secrets while still using HTTP is by encrypting them using a self-signed certificate it generates and supplies. This certificate is not validated by the server, meaning we can generate our own self-signed certificate and retrieve the certificate, the encryption keys from the certificate's endpoint. This can be done without relying on the certificate that the agent originally generated. The certificate is passed in the XMS guest agent public X509 cert, which is a mouthful of a header. And here's the CRL command with that notorious header that can be used in order to fetch the encryption keys from the certificate's endpoint. Now, here's the response we got executing the CRL command on our Azure Linux test virtual machine. And here's the response from the Jupyter Notebook container. And wait, there is a subtle difference. Can you spot it? The format is different. On our Azure Linux virtual machine, what we got back is an encrypted PKCS7 blob, which we decrypted and decoded using a handful of OpenSSL commands. But using the exact same OpenSSL commands on the CertificatesBondPackage got us nothing. So what is the CertificatesBondPackage format anyways? The first thing we did, researching the CertificatesBondPackage format, was to consult Google. We didn't have any answers. And then we thought, okay, maybe someone at Microsoft will have the answer. So we consulted Bing, which didn't know the answer either. But then we thought, the WA agent is the client of the WireServer. It must have some kind of reference to this mysterious format, right? Well, wrong. 0 references. But then we remembered that according to the IMDS, although we are running inside of a Linux environment, our host machine is actually a Windows virtual machine, meaning that all the responses that we get back from the WireServer are meant to be treated by the Windows agent, not the Linux one. Unlike the WA agent, the Windows agent, also known as the Windows Azure Guest Agent, is not open source. But fortunately, it's written in C#, meaning it can be decompiled to something that resembles source code fairly easily. This can be done using a variety of decompilers. We choose ILSpy. And finally, here's the first reference we've seen to the CertificatesBondPackage format, along with its handling code. Shown on screen is a small C# script we wrote to mimic the agent's CertificatesBondPackage decoding. Now, when we executed this script, we expected to get just one certificate with corresponding private key. So you can imagine our reaction, when in reality, we got back 25 certificates with their corresponding private keys, some with very intriguing names. Keep in mind these 3, as we'll encounter them later on in our journey. It is also worth mentioning that one of the certificates and private key we got is for the Asterisk Notebook Cosmos Azure Com domain. This alone already lets us to intercept encrypted SSL traffic to the Jupyter Notebook servers. This is a signed certificate by Microsoft that we have the private key for, after the WireServer simply dumped it on us. At this point, we knew we were onto something. So we got a bunch of certificates we probably shouldn't have, which made us wonder, what's the legitimate purpose for these certificates? At this point, we chose to have another look at the extension configuration we got back from the WireServer. Shown on screen is one of the entries in the extension configuration, specifically the Service Fabric node extension. The Service Fabric node extension had some very interesting information inside of its public settings. As you can see, it has an entry called cluster endpoint, which contained some kind of a URL, and a certificate entry that contained a certificate that we happen to have, the Fabric Quest US1 certificate. When we accessed the cluster endpoint via Google Chrome, an authentication prompt popped up requesting for an authentication certificate. Our best bet was to supply the certificate mentioned in the extension configuration, the Fabric Quest US1 certificate we obtained earlier from the WireServer. So we had our fingers crossed. And bam, what we got back is a huge XML manifest file containing a bunch of cluster information. Let's highlight some interesting points. First, there is another reference to the Fabric Quest US1 certificate, which made us believe that this certificate does have some kind of significance in the context of our cluster. And it also mentioned an HTTPS port 9080, and another reference to that strange keyword, Service Fabric. What is Service Fabric? At this point of our research, we had no idea what Service Fabric actually is. So naturally, we Googled it. And then we encountered this MSDN article. According to this article, Service Fabric is a container orchestration solution. But from this point until the end of our research, we treated it as Kubernetes. Although this is not the perfect comparison, it was good enough for our purposes. So the manifest file mentions port 9080, which according to documentation is a Service Fabric management port. And it also mentions a few IP addresses in the 10.0.0/16 subnet. And according to the IMDS, we're actually inside of the 10.0.0 subnet. And after flashing the IP table rules, we can access other endpoints inside of our subnet. A port scan showed that some of the endpoints in our subnet are listening in port 9080, the Service Fabric management port. We can use the Service Fabric Linux command line tool, sfctl, to try and connect to these management ports. The authentication process requires a certificate. And there seems to be that one certificate that has all the answers, the Fabric Quest US1 certificate, so we decided to try it. Here are the two commands used to authenticate and list all the application instances in our cluster. We issued the last command and wondered, will it work? Well, it worked. The application list command yielded more than 500 Cosmos DB accounts in a regional cluster. And for each Cosmos DB account, we got a bunch of encrypted authentication tokens. But as I just said, all of these authentication tokens are encrypted. They're useless for us. No endpoint will receive my encrypted authentication token. But let me remind you that to this point, we only used a fraction of the certificates we've obtained from the WireServer. So maybe one of these certificates are the one used to encrypt the authentication tokens. So after brute forcing each and every one of the certificates with each and every one of the authentication tokens, we feel a little dumb. Now knowing that the encryption certificate had a pretty indicative name, the Fabric Secret certificate was just the one certificate used to encrypt all of the authentication tokens in our cluster. Just one certificate to encrypt all cross-tenant sensitive authentication tokens. Decrypting the Cosmos DB account key resulted in us gaining the primary key for all Cosmos DB accounts in our cluster. This key is equivalent to the root password for the database, allowing for full unrestricted data access and manipulation. I will now hand over the presentation back to Sagi to demonstrate you the complete exploit chain.
Thank you, Nir. So, unfortunately, we cannot show you a live demo of this exploit because this vulnerability is now patched. But luckily, we were smart enough to record one in advance, so let's view it. Okay, so what you can now see on screen is that the screen is split into two parts. The right part is our research account, which we will perform the attack from. And the left part is the victim Cosmos DB account. This is the Cosmos DB account that we want to take over. You can see that these two accounts have nothing in common as they belong to different organizations. And we will also inspect the access control rules to verify that the research account does not have any special privileges over the victim account. Okay, so what we have to do now is to set up a Jupyter Notebook container and jailbreak it. And we will continue from the part where we already have root privileges inside this container because we've already seen it. So what we have to do now is to remove the local firewall rules, and this can simply be done by executing iptables-f. So let's do just that. And at this point, with the network restriction gone, we can actually access the local service fabric cluster. So we will execute our exploit script, and you can see that our exploit script requires the name of the account that we want to take over. I want to emphasize that this is not a requirement by the vulnerability. This is actually just a precaution that we took while developing this exploit in order to make sure we do not access any data that is not our own, even by mistake. The vulnerability itself actually lets you list all of the accounts in your cluster, and you can simply pick and choose which account you want to take over. So once the exploit finishes running, you can see that it dumps on you the plaintext key of the Cosmos DB account. And if we'll compare it with the key that you can find in the management panel, you can see that they are identical. Okay, so let's quickly recap everything that happens behind the scene in this video. First, we set up a Jupyter Notebook container and jailbreak it by obtaining root privileges on it and removing the network restrictions. Then we query the WireServer in order to obtain two main things. The first thing is the extension config, which we can extract the cluster manifest from. And the second thing is the certificates endpoint, which we can extract a bunch of certificates from. One is used to connect to the local service fabric cluster, and the other one is used to decrypt the encrypted authentication tokens we get from the local service fabric cluster. So you would think that we'll be done by now because we already achieved so much, but we didn't stop here. We only used a fraction of the information that the WireServer dumped on us, so let's see what else we can find. We had another look on the extension config and the cluster manifest, and this is a snippet from the cluster manifest. And you can see that we have a couple of connection strings here to some Azure storage accounts, but these Azure storage accounts, these connection strings still require some sort of a key. So we were looking for this key, and we actually ended up finding it inside the protected settings of one of our extensions. And these are the OpenSSL commands that we used in order to decrypt these protected settings. And as you can see, here is the plaintext key. So we now have 4 connection strings to different Azure storage accounts, and these are the accounts. Now, since these are Azure storage accounts, it only makes sense to explore them using Azure Storage Explorer. So let's do just that. This is what the Azure Storage Explorer interface looks like when you connect using these connection strings. And generally, we found there like hundreds of gigabytes of metadata regarding customer environments. But the most interesting things that we found there was actually a log file that indicated that the IP addresses in the 10.0.0/16 subnet may have an external interface, a public IP address that you can access from the internet. Now, we thought, this might be reasonable. Perhaps Microsoft had their design where this makes sense. But in any case, access to this IP address must be allow listed, right? I mean, there should be absolutely no reason that I will be able to access this IP address from my office, right? Well, wrong. Turns out that we were able to authenticate to this public IP address from our office over the internet and view the underlying service fabric management panel. And this is what it looks like. Now, just to make sure we all understand, this is some internal Azure infrastructure that we can access from our office over the internet. At this point, we were thinking, this can be the only endpoint that is accessible from the internet, and that there must be more endpoints like this. So we decided to scan the internet for the Service Fabric management port, which is 90,080, and see how many Service Fabric instances would let us authenticate using our favorite certificate, the fabric.westus1 certificate. And to our surprise, over 100 Service Fabric actually let us authenticate using that certificate. And even though we used the WestUS1 region certificate, we actually managed to authenticate to different regions and even different services. Now, At this point, we think that Service Fabric is a core component inside Azure and is used to do a lot of things behind the scenes. I will now hand it over back to Nir to summarize our findings.
Thank you, Sagi. Let's talk about what we found and what is the impact. We managed to retrieve multiple kinds of authentication tokens that allows us to access and manipulate customer data in multiple access vectors. The first one is the Cosmos DB account key, which after decryption is identical to the primary key of the Cosmos DB account. As you can see, this is the key from our exploit output, which is identical to the primary key found in the management panel. And as I said before, this key is equivalent to the root password for the database. Another authentication token that we have is the notebook auth token. We can use this token in order to gain arbitrary code execution on the Jupyter Notebook container. And after using this access, we can extract the database secrets from there. As you can see, this is how we executed the IT command on the Jupyter Notebook container using that token. The last token that we'll talk about is the notebook storage account key. We can use this token in order to manipulate existing saved notebooks, potentially making the victim executing queries on their database without even knowing. We confirmed that all of the authentication tokens can be used in order to access the databases of thousands of Azure customers, including numerous Fortune 500 companies. Along the way, we also retrieved Microsoft signed certificate that allows us to intercept SSL traffic to the Jupyter Notebook servers. And we retrieve connection strings for two internal Azure storage accounts that may contain customers' environments metadata. Overall, we believe we proved a high degree of control over the entire service, especially when this access can be maintained without accessing the vulnerable environment, but instead from the internet. So let's quickly overview the disclosure timeline and our work with Microsoft. On August 9th, we first managed to exploit this vulnerability. And 3 days later, we already sent the advisory to Microsoft. We understood that this is a very severe vulnerability, and we wanted to let Microsoft know as soon as possible. 2 days after that, we noticed that Microsoft has already mitigated the issue. The way Microsoft chose to address this issue is by removing the Jupyter Notebook feature altogether. This is an extremely fast patch. Less than 48 hours after our initial report, until the Jupyter Notebook service was disabled to all Cosmos DB customers. 2 days after that, we first heard back from Microsoft confirming our reported vulnerability, and on the same day, we started seeing that some of the obtained credentials we obtained during our research, things like certificates or passwords, are starting to be revoked. And a day after that, Microsoft awarded us with the maximum bounty available for Azure, $40,000. Which we plan to donate. This is the fastest bounty we've ever seen from Microsoft, only 5 days after our initial report, which was on a Friday. On August 23rd, we had a great Teams meeting with the Microsoft team where we discussed mitigations, and they confirmed to us that there are several thousands of customers that are impacted by this vulnerability. And on August 26th, Microsoft emailed all undeniably affected customers, instructing them to regenerate their access keys. This is unusual in the cloud security world. One of the reasons that customers choose cloud solutions is because the security is managed by the vendor. But in this case, customers had to take manual actions in order to make sure that fully mitigated from this issue. And I mentioned that Microsoft only emailed undeniably affected customers. What do I mean by that? Microsoft chose to email only customers that had the Jupyter Notebook feature enabled during a research period, which lasted like less than a week. And we think that Microsoft should have emailed all potentially impacted customers, because although this vulnerability is now patched, you can never be sure that this vulnerability wasn't exploited prior to our engagement. So just a quick TLDR of our entire engagement against the Cosmos DB service. We first jailbroke the Jupyter Notebook container by elevating our privileges to root and then removing all network restrictions. We then used this unrestricted network access to contact our host machine WireServer and obtain 25 certificates, which we only used a small portion of. We then used some of these certificates in order to authenticate to our local service fabric cluster and list all the Cosmos DB accounts in our cluster, including their credentials. We then proceeded to use the same certificates in order to connect to other Cosmos DB-related service fabrics over the internet. And after less than a week of intensive research, and with this kind of level of access, we felt like we had to report our findings to Microsoft. But all in all, we think that this is as close as it gets to a service takeover. So yeah, this is the story of ChaosDB, the vulnerability that allowed us to hack the databases of thousands of Azure customers. Thank you. Are there any questions?
Did they change any of the authentication to stop
We were requested that any question will be taken from the microphone in the back.
The microphone is over here. Sorry, it's taken. Nice.
There's another one over there.
Yes, we can battle over them. Nice findings. Would you be able to assess in any way what kind of business data you were looking at for those companies, Fortune 500 companies? What kind of, or would we be talking about everything, game over?
So we really tried hard not to access any data which are not
Sure,
not our
that's
own.
why I'm trying to
But yeah, you can think about all the data you can find in your everyday database. Everything that you can imagine can be found in these databases.
Yes, so let it be noted, I think the bounty you received should have been per each affected for Fortune 500 customer.
Hi. Did Microsoft give you any feedback about how they changed the authentication afterwards to stop one certificate being so powerful, for example?
So we only saw that our certificate was revoked and cannot be used anymore. And we weren't able to obtain new certificates because they disabled the Jupyter Notebook feature completely. So we have no idea if they changed the mechanism behind the scenes. But this is how it worked back then.
Okay. And there's no indication that they're going to reinstate that Jupyter Notebook functionality?
What do you think?
I have no idea.
You don't know.
Thank you.
Hi. First of all, thanks for this interesting and also entertaining talk. I wondered, like when you did the privilege escalation from the container, do you know whether Microsoft noticed this somehow or monitored it? Because I know that it's possible to monitor, for example, Azure containers also in Azure Security Center. So wouldn't it make sense for Microsoft to monitor for such kind of jailbreaks?
So yeah, the container itself had no monitoring systems inside of it. We can only speculate what happened like the outside of the container, but there is no like any additional Microsoft solutions that monitor such a situation as you suggested. So probably not.
Okay, thanks.
Okay, I think we're done. Thank you.
Thank you very much.